Hello everybody. Welcome to the Deep Learning Models video in the Large-Scale Machine Learning section of ML Expert. As a refresher, this is a basic neural network. So here we have our capital sigmas, which will take in the inputs x1 and x2 multiplied by the respective weights and sum the results of the connections to that particular sigma. So here, this sigma would represent x1 times w1 plus x2 times w3. Those would feed in to this sigma. And here we have that written out. The same pattern would follow here with this sigma. After that, these would be fed into the sigmoid functions. The same pattern that we had over here would follow here. The only difference now is that these inputs are actually outputs of the preceding neurons. This entire result will be put through a final sigmoid here to produce y hat. After this forward pass is complete and we have this y hat that's used to determine the gradient of the loss with respect to all of the weights. We do this by backpropagation. After we have all of the gradients of the loss with respect to each weight, we can update each respective weight in terms of its gradient. Here is that weight update function. If you need a refresher on this, feel free to watch the neural network video in the machine learning crash course. Now that we understand the basic neural network model, let's go ahead and look at how we would represent these computations in a machine. So here we have our machine, we have our RAM, which is our memory, and then we have our CPU. The RAM would store the mini batch of examples, so here we have the X features and the Y label. The CPU would fetch the example from RAM, and then it would do the forward pass with this example. Now how this is actually done in terms of computation is a matrix multiplication. So how we get that is if we have our x1 and x2s and all of our weights, we can put x1 and x2 in a vector, and we can put all of these weights in this matrix. And if we multiply these together, we'll get x1 times this plus x2 times that. Following through with the rules of matrix multiplication, we'll then have these terms here. And then finally, we will add these terms and these terms to get this result. So now we can effectively represent these interactions with matrix multiplication. Now, matrix multiplication is used in order to take advantage of highly optimized linear algebra libraries, which have efficiently implemented matrix multiplication. An example of one of those libraries is basic linear algebra subprograms. This is more or less the standard when it comes to linear algebra. Now, as well as the forward pass, matrix multiplication can be leveraged during the backpropagation as well. Alright, so now the CPU will get this feature label example from RAM. It will do a series of matrix multiplications that will generate a loss. Now the result of those multiplications will be a prediction, or y hat, and we can use that y hat to generate a gradient with respect to the loss function. Then the CPU will place that loss back in RAM, and it will grab another example. It will continue this process for all of the examples in the mini batch, and then it will take all of those gradients that it obtained from each example and add them up and put the total mini batch gradient back into RAM to be used for the weight update. Now, while we're on the subject of low-level operations such as matrix multiplication, let's go ahead and talk about how even a convolution can be seen as a matrix multiplication. Now, if you recall from the machine learning crash course, a convolution is performed when we filter a particular image with some kernel. So here, x1 prime is obtained from multiplying together w1 and x1 and adding that to all of the products of all of the other elements in the overlapped kernel and image. We would then slide this kernel across the image to generate x2 prime. We would slide it down then to generate this here, and then finally we would finish the convolution operation by solving for x4 prime. So the thing is that this takes 4 steps. Instead, what we can do is we can flatten out this kernel matrix here. So here it's the same exact kernel matrix, it's now just been flattened out. And if we flatten out the section that we would have overlaid it with as well, and flatten out all the other subsections, and we multiply this matrix times the flattened out kernel, we get the result of the convolution. So that's generally how we more efficiently can perform convolutions to some image with some kernel without stepping through each subsection of an image. This allows us to use those efficient linear algebra libraries that we talked about earlier to even implement convolutions. So fully connected layers and convolutions are called operators. So it's important in large-scale machine learning that the operators we use are highly optimized. And in our case, this typically happens through concurrency. So maybe in the machine learning crash course, where we would have said that a convolution happens stepwise as we slide the kernel over the image, in terms of concurrency, we would execute effectively all of those steps or the entire image at one time. Now, as opposed to concurrency, we can also have parallelization, which is also extremely important in terms of large-scale machine learning. So how does that look? Now, we went over earlier when we had a single machine with a single CPU, but what if that machine had multiple CPUs? In that case, each CPU could grab an example from the mini batch, and then they could independently calculate the gradient with respect to their individual example. They could store that in RAM, and then a single CPU could grab all of those individual gradients, add them up to get the total mini batch gradient. It could then store that result in RAM to be used for weight updates. Now, this can often be implemented through software such as Open Multiprocessing or OpenMP. This would help coordinate all of the processes across each of the CPUs. This is especially true when we have a shared memory. Alright, so CPUs generally have more than one core, which means it can handle more than one task at a time. Earlier we drew CPUs as being able to just handle one example, but if they have multiple cores, then we can actually apply more than one example to each CPU. So in general, CPUs are really fast, but they have low bandwidth. So let's say that we have 100 million training examples, and each example takes 1/10 of a millisecond to compute. That would be the forward pass, the backpropagation, and the weight update. So let's say that we have one CPU, and that one CPU has 4 cores, so that means effectively it could handle 4 examples at the same time. This would still amount to 45 minutes per epoch of the data. Let's say that we wanted to train on 10 epochs, that would take almost 7 hours total just to train a model. That wouldn't even include hyperparameter tuning, which could increase this time by 10 times. So again, CPUs are pretty fast in terms of how fast they can calculate something. It's just that their low bandwidth or low throughput doesn't quite support 100 million examples. Now, this is a case where we could turn to a GPU, or a graphics processing unit. A graphics processing unit will be a peripheral component to the CPU, such that a machine with a GPU could look like this. It would have the RAM, the CPU, and now a GPU. So what is a GPU? Well, a GPU is going to have multiple streaming processors. Each of these streaming processors will have a series of cores. For our use case, we can consider these cores to be the same as the cores in the CPU. Now, some rather expensive GPUs can have over 50 streaming multiprocessors and over 60 cores per streaming multiprocessor. Now, unintuitively, graphics processing units are typically slower than performing a calculation on a CPU itself. Let's look at an example. If we have an example in RAM and we send that example to the CPU, we have to then send that example to the GPU. The GPU would then calculate that gradient. It would pass the gradient back to the CPU and pass that back to the RAM. So what's the actual benefit here? Well, the bandwidth is much larger. So even though it's slower than a CPU would be for a single example, we can do many more examples at a single time. So let's say that we have 100 million examples, and this is 10 gigabytes of data. Now let's say the bandwidth between RAM and CPU was 25 gigabytes per second, and let's say the bandwidth between the CPU and the GPU was 8 gigabytes per second. Well, in that case, it would take a few seconds for us to get our data into the GPU, and let's say we could fit all of the data at a single time in the GPU. So let's say this GPU can hold 16 gigabytes, our data is only 10. Now, if this GPU had 56 streaming multiprocessors, and each of those had 64 cores, then that means we could do 3,584 computations at a time. let's say each computation still took that tenth of a millisecond. So let's say it could calculate something as fast as a CPU could, and ignoring some overhead for simplicity, then an entire epoch would take about 3 seconds to perform in order to find the overall loss for that data. Now again, we typically do many batches, but this is just an example. So the GPU would send that data back to the CPU, and that CPU would send the data back to the RAM, and it would still have to follow those same bandwidth limitations. And if we did 10 epochs, let's say, that would only take 30 seconds. So in general, if we accounted for the time it took to transfer the data from the RAM to the GPU, as well as the time it took to perform 10 epochs, it would take 34 seconds total compared to the 7 hours with just the CPU. Now, let's say that all the data wouldn't have fit in the GPU, or we did want to do more mini batches, this time would go up, but it would be very unlikely that it would even take a tenth of the time as the CPU. Now, this was a simplified example, but the orders of magnitude difference typically holds up in the real world. So a natural question is, can we have multiple GPUs just like we had multiple CPUs? The answer is yes. We can even have something like this. Now, in general, since the CPU has to be the organizer between all of the processing of the GPUs, the CPU usually ends up being the bottleneck. So there are different configurations we can use. So this one is more or less a cube, and how this works is we eliminate the CPU as the bottleneck by allowing the GPUs to talk directly to one another. This can be accomplished through technologies such as NVLink, which is a way to give direct memory access from a GPU to another GPU. This can result in terabytes per second of throughput. Alright, so from here on out, we'll address CPUs and GPUs as interchangeable. So what if we can't fit our data in RAM? So let's say that we have 200 features per example, that brings us to 80 gigabytes total, and let's say that we have 1 billion examples instead of 100 million. Well, in that case, we won't be able to fit it in RAM, and we'll now have to have some hard disk drive that we would store it on. The problem is the bandwidth here, let's say the bandwidth from the hard disk to the memory was 100 megabytes per second, then 98% of the total training time would just be spent on transporting your data. This typically isn't a great way to do it. Another option could be to vertically scale this machine up and just keep adding GPUs or just keep adding CPUs such that we could eventually fit these things on a single machine. This would be similar to a supercomputer, but those are typically very expensive. So another option could be to spread our 80 gigabytes across 8 machines. So each machine would get 10 gigabytes. So let's see how this would work. The CPUs would generate the gradients for each part of the 80 gigabytes of the data, and then they would ship all of the data to either neighbors or maybe a direct connection with a single machine. This single machine would aggregate all of the partial gradients into a total gradient with respect to the loss so that we could then update the weights of the model. They could communicate via Ethernet, or they could directly communicate with the memory of the devices by using technologies such as InfiniBand. Now, this may sound extremely similar to Spark, and it effectively is. One reason that we may not want to do something like this, or use Spark, is because it's going to be synchronous. So let's say that a single machine goes down, here machine 5, now machine 1 has to wait until machine 5 becomes available. Let's say either the network goes bad or the machine itself goes down, the entire training process is halted just because a single machine went down. Now, if we had 1,000 machines, it's likely that at any given time, a machine will be down. So this isn't always a viable option. So another thing we can do is forget the synchronous property. We could instead have a single machine responsible for keeping track of all of the parameters or the weights. This would be called a parameter server. And each worker machine would pull the current parameters of the model from the parameter server. It would then pull some queue for examples, or maybe fetch the examples from a database, in order to find the gradients with respect to the examples it found, given the current model weights. Now, whenever any of these machines finished up finding their gradients, it would then ship the gradient to the parameter server, and the parameter server could update the weights. And then those machines that just sent out the gradients would then refetch the weights from the parameter server. This would happen completely asynchronously, such that at any given time, a worker could be sending its gradients, and another worker could be receiving the most recent weights. This is called the parameter server topology, and one implementation of this is called downpour stochastic gradient descent. So a couple good things about this is that if a node were to go down, then we could just replace that node and assign that same work to another machine. Now, one problem with this is that most likely these machines will have stale parameters. That means when we're receiving a particular weight from the parameter server, it could be such that there are more recent weights to be made available within a few seconds. So this means that these models could be executing their mini batches on old model parameters. Now there's a few ways to mitigate this. Some systems implement something called a barrier, which makes sure to synchronize machines if any one machine falls too far behind in terms of the most recent model parameters. But in practice, this does generally work well, even though we have this problem of staleness. Now, more often than not, we will have more than one parameter server, and these parameter servers will have different workers assigned to them. Now, the type of parallelism that the parameter server introduces is called data parallelism. What this means is that the model is the same for each machine, but different data in different mini batches go to each machine. So effectively, we're parallelizing the data across many machines, but every machine has the same model. Again, this is discounting the fact that sometimes the models can be outdated due to parameter staleness. So this is what we'll do if the data can't fit in the RAM. Now, if the model can't fit in RAM or GPU, then we want to partition our model across different machines. So here, this machine could get a part of the neural network, this machine could get another part, and so on. Now, in order for a forward pass or backward propagation to still work, these machines will have to communicate at these points. Generally, this will work better with convolutional neural networks than fully connected networks. For instance, if every node was attached to every other node, then a lot more communication would have to be done here. But in terms of convolutional neural networks, if we have a small receptive field or small locality, that means that there will be less communication across machines. This will make the entire process more efficient. Another way that we can introduce model parallelism, as opposed to data parallelism that we had with the parameter server, is to split up the model by each layer and distribute each layer to a separate machine. Now, intuitively, this may not make sense. This layer would have to complete before this layer could start, so what's the point of parallelizing each layer? Well, what we can do is something called pipelining, where this example would go in, followed by another example, and followed again by yet another example. What this means is that at any given time, each machine is calculating its own independent example, and the same would be true for the backward propagation. Now, what if the model and the data can't fit in RAM? Well, we can combine them. So here we have the parameter server architecture combined with the model parallelism architecture. We can also introduce pipelining, but in this case, we're just distributing sections of the model across each machine. Now, some things we want to think about here is intermittent backups. So maybe this cluster will have backups to its calculations such that if any of the machines were to go down, upon replacing that machine, we don't have to recalculate different checkpoints that we could have had if we had done backups. Now, one implementation of such architecture is called Project Atom. Now, the parameter server is an example of a centralized topology. One of the problems is it can require a lot of network bandwidth. Oftentimes, with many machines, we'll anticipate needing 50 gigs of network bandwidth. Now, there are ways to mitigate these steep bandwidth requirements by limiting the communication between the parameter servers and the workers. For instance, instead of each mini batch example that a worker gets, updating the parameter server, it could instead pull a few mini batches from the queue or the distributed file store that it's pulling from, and after it calculates a few, maybe 3 or 4 mini batches, then it can update the parameter server. Here, we're trading off staleness for less communication. And there also has been some work on how we can compress or send less data to the parameter server and still achieve the same results. Some examples here, so TensorFlow has a parameter server, and you can also have a parameter server with MXNet. Now, as opposed to these centralized topologies, we also have decentralized topologies. Now, in this example, there is no leader or parameter server, for instance, but each machine will still get a section of the mini batch. So here, each machine would calculate the gradients, just like we saw before, and then each machine could communicate with every other machine to communicate its own gradient such that every machine now has the total gradient and every machine can update each of its weights appropriately. The problem is bandwidth is typically the limiting factor and makes this not a great strategy. So one thing that we can use is something called ring reduce. Now, for an example of ring reduce, we'll go ahead and get rid of the machines here, and we'll actually put values to these gradients. So here, let's say that each mini batch had 16 examples. Since there's 4 machines, each machine would get 4 examples, and these elements are each the gradients with respect to each example. Now remember, the goal is to equip every machine with everyone else's total gradient. But for now, each machine just has the gradients with respect to its own examples. So in order to more helpfully display the algorithm, we'll go ahead and color code each gradient. These colors indicate which machine will send which element first. So this machine will send the 13 first, this machine will send the orange 18 first, this machine will send the 3 first, and this machine will send the 2 first. The receiving machine will add up whatever value gets sent to it with that respective element. So here, this 2 will be added to the 13 will be added to a 3, the 18 will be added to the 2, and the 3 will be added to the 1. Then we move to another element. So here the 15 gets sent, here the 16 gets sent, the 20 gets sent, and the 4 gets sent. The receiving machines will just add their respective numbers, and then we send another element, and again, those will just be added to each respective index, and now each machine has one of the sums of the color-coded variables. Each of the machines will just send its known information in a ring fashion. So here, the 38 will come here, the 31 gets sent there, the 27 gets sent there, and the 21 gets sent here. And this just continues for each of the elements. And now, if each of the machines sum each of these arrays, then every machine will have the total gradient obtained by the entire mini batch. The reason why this way is preferred over every machine sending every other machine what it has is because this requires far less bandwidth. In fact, ring reduce is often called bandwidth optimal because each node's total communication doesn't depend on the number of nodes in the ring. This is opposed to the parameter servers or the peer-to-peer configurations, which do depend on the number of nodes. Now, this bandwidth optimal configuration allows majority of the computational time to be spent on actually calculating the gradients and a minimal amount of time on transferring data. This allows almost a linear speedup in terms of the number of GPUs that we add to the ring. So one implementation of ring all reduce is Horavad, and that was developed by Uber. Now let's move to an example where we compare CPUs versus a GPU versus many GPUs. Alright, so here we have our Jupyter Notebook. Now this is within AWS SageMaker, and I've bought time on an AWS instance which has 8 GPUs. So here we can see that we have 1 CPU, and as well we can see that we have 8 GPUs. Now, in reality, we would never use this type of machine with just this tiny amount of training data here, but this is just for example purposes. So here we are building a simple model using TensorFlow, and specifically we're using the Keras high-level API on top of TensorFlow to help get us this sequential model. Now, the sequential model has layers, and these layers represent the layers that we talked about in the neural network. So here is our first layer. It's going to have inputs of 3. So this would be each of the features here. Now it's going to have 5 neurons in the hidden layer with its input of 3, and it will have a ReLU activation This layer will feed into this layer, which will only have 3 neurons. And finally, those 2 layers will finish off with this one layer here, in which we just have 1 neuron, and that will have a sigmoid activation function. We assign our optimizer to be stochastic gradient descent with a learning rate of 0.01, and then we compile this model that we've created with our optimizer, specifying our loss, which in this case is binary cross entropy. And finally, we can list some metrics that we want to print out. And here, one of those metrics that we want is binary accuracy. You can think of this as just normal accuracy. All right, so the first thing that we'll do is I'll go ahead and pick my device. So here I want to use CPU 0. So we listed out all the CPU devices, and we can see here that we got / physical device CPU 0. So we can reference this device with this identifier here. It's just whatever is after that physical device. And once we reference this device, we can fit or train the model with the training features and the training label. Now we'll specify here to take 20 epochs. So let's go ahead and see what this would produce. Here we have all 20 of our epochs. We are printing out our loss from our loss function, and then we have our binary accuracy printed out as well. Now, in addition to this, we can switch our device to use one of the GPUs. So here I'll just use GPU 0. Again, this is listed up here from when we listed out our GPUs. So here, GPU 0 is listed. So now we'll train our model with the GPU device, and we'll still see the printout of the 20 epochs here. One thing to notice is that the loss in terms of the CPU took some time to come down to this 0.68 here. And the GPU looks like it hit that same loss or converged to that same amount of loss a lot faster. That's just something interesting to note here. So we've gone over CPU, we've gone over what that looks like against a GPU. Now let's see what it looks like to send our data out to multiple GPUs to be calculated in parallel. So here we're going to use something called the mirrored strategy, which is supplied by the TensorFlow distribute library. What this effectively means is that each GPU will mirror one another, and what each GPU will do is have a model defined, we'll have our optimizer defined, and we'll compile that model. Now outside of this strategy scope, this mirrored strategy, we can fit the model. And I've turned up the debugging here a little bit to tell us a little bit more about what's going on. So here, when I called fit, we have the info telling us that we're using the mirrored strategy with the devices that we have already seen up top when we listed out our devices. And then for our second epoch, after everything is set up, we can see a little bit more concisely what's happening. So we can see all the different GPUs here, 0 through 7, fetching data or generating different parts of the dataset. We can see our loss and our accuracy just as we did before, except now these losses and accuracies will be generated across all of these GPUs instead of just one of them. Now, if we scroll all the way down to the bottom, we'll see that we ended with a binary accuracy of 80% and this loss. One interesting thing to note is that the other examples, when we just used a single CPU or single GPU, we could only get an accuracy of 0.6, and our loss was a lot higher. So that was a quick demo on the differences between a CPU, GPU, and multiple GPUs. All right, so in total, we've talked about operator level concurrency. This would be with the convolutions and the matrix multiplications on the forward pass and back propagations of neural networks. We then talked about model level parallelism. This would be when we distribute either models or data across a single machine in terms of its multiple CPUs or multiple GPUs. And finally, we talked about distributed training, where we have multiple machines which could have multiple CPUs or multiple GPUs. That wraps up the deep learning models video in the large-scale machine learning section of ML Expert. Thanks for joining, and we'll see you next time.